So thanks everybody for joining. Today we are going to be discussing all things sodium-ion. Quick introduction for those of you not familiar: Supply Chain Insights as a specialist lithium-ion supply chain research and consultancy. We do a huge amount of work on due diligence, corporate strategy, lenders market reports, and also a lot of term sheet and offtake contract advisory across the supply chain, in addition to a regular supply, demand, cost and price forecast outlook. If you'd like any more information on that, please feel free to scan the QR code or reach out to my colleague Derek, whose information is on the first slide. So today we are going to be welcoming Frank Wunderlich-Pfeiffer, who is very excited to be here. We're very excited to have him. Frank is an expert on all things sodium-ion. He's been following the market since about 2017 as an independent analyst and consultant. And, over the past couple of weeks, we've been having a lot of discussions about what sodium-ion means to the future of energy storage, and also in particular to the lithium-ion battery market, which is currently the dominant market for electric vehicles and energy storage systems. So we'll be talking a little bit about an introduction to sodium-ion, some of the history to put the context together, and then also looking at the impact that it will have in terms of market disruption on lithium-ion, how quickly that's likely to be, and how that's likely to develop both in China and outside of China. If you'd like to know more from Frank, please do follow him on Twitter, or also you can see some of the links to his work there on the screen as well, which will be made available afterwards. So with that, Frank, I will pass over to you, and let me know when you want the slides changed.
Thanks. How about now? Thank you. Well, hello. I do want to give a little bit of an introduction into the technology, but before we go to sodium, let's have a little word about lead-acid batteries of all things. For a simple reason, lead-acid batteries have a market of about 450 gigawatt hours per year, which is more or less the same scale as LFP or NMC, give or take 100 gigawatt hours or so. So it's quite huge, and it's very strange that this hasn't been, that this has never been replaced completely, even though it's 160 years old. And the reason, if you go back into the history, is actually quite simple. You can see a lot of nickel in there. Nickel cadmium, nickel iron, later nickel hydrogen, and then nickel metal hydride. And the problem is really the nickel. On the one hand, the other problem is it was using water as an electrolyte, which meant that, well, the voltage wasn't very high, and low voltage means you don't have very high energy density, because every single electron needs a nickel atom to pair with in the cathode, and that just means it's very heavy, because the voltage tells you how much energy you get for each electron. And so it's not a very promising technology, even though you could say that all these nickel batteries are in fact something like hydrogen ion batteries, and hydrogen is much lighter than either lithium or sodium. So it's not always so easy. A lot of people are worried that sodium ion batteries cannot be any good because sodium is 3 times as heavy as lithium, but please do keep in mind, in your typical lithium-ion battery, NMC battery, the lithium makes up about 3% of the total weight. For LFP, it's even less. And if it's 3 times heavier than that, it's still not very much. So the weight of the sodium really doesn't matter too much. Sodium entered the battery space in 1966. Under the direction of Ford. Ford sponsored the research back then on sodium-sulfur batteries. They were looking at building them for electric vehicles. Unfortunately, it wasn't a very good technology for that purpose, because it was a high-temperature battery. We're talking about 350 degrees Celsius, so much hotter than your typical oven. And that really wasn't very good for that purpose. But that wasn't the first time that Ford was going for electric vehicles. Actually, back in 1914, they were cooperating with Edison, who had developed the nickel ion battery. to make electric vehicles, but because of the World War, that didn't go anywhere. Nickel iron, you see, is a technology that was developed right after nickel cadmium, because people realized, yeah, nickel cadmium won't cut it for any large scale applications, even though it had really great energy density, twice as much as lead acid batteries. But cadmium is rare and fairly expensive. Toxicity, nobody cared about that. Yeah, iron was much better for electric cars, also had much better cycle life. Unfortunately, energy density was only half that of lead acid batteries, so you can kind of imagine what kind of car this would have been. But in the early 1900s, it might have been fine, even though electric cars even then were quite expensive. Things changed in the 1970s and 80s with when people moved away from the high temperature sodium-sulfur batteries. Sodium-sulfur is the one kind of battery that they realized back then. They really wanted to use lithium-sulfur, but they would have needed 450 degrees Celsius for that, and that didn't work. They ran into corrosion troubles, and so they couldn't do it. So they switched over to a much better and more practical design idea, which used solid cathodes and anodes instead of molten sodium and molten sulfur, which is really just an explosion waiting to happen. And used organic electrolytes and yeah, a newly discovered kind of cathode, the intercalation cathode, and that was actually a result of research in superconductors. But in the end, John Goodenough had the idea, hey, let's use cobalt oxide, and cobalt oxide it was. And in 1991, Sony came out with the first lithium-ion battery. Wasn't the first lithium battery. Unfortunately, Molly Energy had a lithium battery with a lithium anode out before that, which was so explosive that nobody wanted to call their batteries lithium batteries anymore. That's why we are calling them lithium-ion batteries now. They not only had good cathodes, the cathode lithium cobalt oxide, that was a choice. Nobody cared about the raw materials. Raw materials were did not figure into the price so long as you didn't use gold or platinum or something like that. The manufacturing costs were the dominant factor at the time. So if you want to have a battery, you use the best materials available. Sodium was slightly worse, but it had been in development alongside lithium all the time, going back to the 60s, in the 70s, in the 80s. Actually, in the 70s, sodium metal oxide was the first kind of potential cathode material that was in research. But yeah, it would not have made sense to commercialize a sodium-ion battery in the 90s because the production cost was just too high. Of course, that changed. There was some development. Graphite anodes for lithium came in 1994, which is a scourge, you could say, because it is responsible for a lot of the downsides of lithium-ion batteries. But also for the fairly high energy density that was realized with it. So it's always a compromise, no matter what you do. Everything in batteries is a compromise. Lithium iron phosphate was developed in 97, practically then in 2001 when the carbon coating was developed, and it took a little while for them to commercialize. In 1999, there was finally a proper good anode, at least for sodium-ion batteries, that was described and researched by Jeff Dahn, whom you might know from being sponsored by Tesla these days for his battery development. Hard carbon used to be the next big thing in the 90s as a replacement for graphite, because potentially hard carbon can be better than graphite, even for lithium, but this never came to be. Graphite became so popular and so good that the research kind of fell flat. I should also say I talked to quite a few researchers and who were researching batteries in the early 2000s, and they said, yeah, practically the field was dead. nobody cared about batteries. And there was very little research going on, very little money available for it. And that's why there was actually little progress. In 2001, NMC cathodes came along. They weren't really used until somewhat later when cobalt became too expensive. Good cathodes came along then around the 2010s. Prussian blue was developed by Good Enough in 2010. 2011, first startup was, or first research in practical batteries for that started in 2012. 2011, Faradion was one of the startups that formed around sodium-ion batteries in Great Britain and was one of the most advanced companies. Unfortunately, not one of the most supported financially. They typically had a budget of less than $1 million per year. And it's not the kind of budget that you need in order to get an industry started. And that happened when lithium prices shot up by a mere 1,500% in 2021. And that changed everything. Heiner announced their batteries back then. They had been in development for several years back then. They were definitely at the forefront in China in developing them. And yeah, one of the, I took an example that is more or less the worst you can expect for a battery pack for EVs from sodium-ion batteries. It's using the 32140 cell, a cylindrical cell that's basically optimized to be used air cooled. So it's very simple, and the battery pack, this kind of battery pack is being used in the E10X electric vehicle that they also presented at the time earlier this year, which is a subcompact car. It's somewhat larger than the Wuling Mini, seats 4 passengers, regular car. But when you look at this battery pack and keep in mind that each of the cells is about 14 centimeters long or about 6 inches, then you quickly realize that the width of the battery compartment is on the order of 75 centimeters, 2.5 feet. So it's very narrow. This kind of battery is, the capacity of this battery pack is so low, not because the energy density is lacking. It's so low because the manufacturer of the car decided that's all the cells they could afford to put into this car to keep to meet their price point. And that's the typical story. So it's very easy to get a false impression that sodium-ion batteries are only capable of running small cars. And you can see the pack density at 120 watt-hours per kilogram, and you can get very decent cycle life of 2,000 to 3,000 cycles, which is typical. These batteries are simply developed to meet these criteria. Next slide. Yeah, I just as an example, what could you do with these very first generation batteries that are not really the best, even from Heiner? If you go back to the 90s and you look at the General Motors EV1, it had a battery pack with 30 watt-hours per kilogram. That was lead acid batteries, 90 kilometers range by modern standards. And you could have made a car with 360 kilometers range, and I think GM would have been very happy to use these batteries back in their day. You could do something similar with something like the Tesla Model 3. Obviously, if you use the battery pack like the one I've shown this wouldn't work because it's not very space efficient, but there are better constructions that could actually fit into the battery compartment of a Tesla Model 3. You would obviously have to redesign it, but you could definitely get something like the 350 kilometer range. The first LFP pack of Tesla had 125 watt-hours per kilogram, not because that's how much they needed. It was because that's when the subsidies, the Chinese subsidies, were only granted if you had at least 125 watt-hours per kilogram. But Tesla would have been just happy to use 120. It would not have played much of a role. It would have made a difference 18 kilograms for a 1,800 kilogram car, so maybe 1% weight difference. So that would have been fine. So when you look at sodium-ion batteries and you think you cannot use them in proper cars, keep that in mind, that even for very simple batteries of the very first generation that's on the market, you could do something like that without much trouble. Next slide, please. Yeah, as to sodium-ion batteries, in general, pros and cons, a lot has been talked about the energy density. It's obviously lower because sodium is a bit more, is a bit heavier. It also provides slightly lower voltage in general, about 0.35 volts less than lithium. With your typical cell voltage of 3 volts or so, that means that you lose about 10% of the energy compared to a theoretical battery that just replaces lithium for sodium. The additional weight then also has an impact. The other problem is, of course, there's less industry experience. It's kind of hard to find customers right now, but this is all going to change. If you can deal with the somewhat lower energy density, that will improve. You can see it down in the bar that sodium-ion batteries are right below LFP right now. They're actually at the level that you would have expected for LFP about 5 to 10 years ago, I'd say. And in the next few years, it's going to catch up to LFP, and it's not going to stop very easily at that point. It can, at least the technical potential is a lot higher than that, which is similar for lithium. You can look at your typical NMC batteries, 230 to 280 watt-hours per kilogram. That bars at scale roughly. There's a lot of potential improvements that has already been announced. This is just what has been announced commercially right now. These 500 watt-hours per kilogram earlier this year at CATL. In the labs, you can see higher figures already. Technically feasible from a theoretical standpoint, you could get over 1,000 watt-hours per kilogram with lithium-sulfur in particular. Figures for sodium are significantly lower than that, but much higher than what's currently being made. In general, what you do get with sodium is faster charging. That has a simple reason, has two reasons. One, you don't use graphite. Graphite is really bad for charging speeds. And also sodium, it's a bit paradoxical. Sodium is bigger, but it can move faster in electrolytes. That's because of the charge density. Lithium is a very small ion, and it has very high charge density. So at the surface of the lithium ion, you have very strong forces pulling everything towards it. And so it's pulling all the molecules from the electrolyte towards the lithium ion. And so you have a very rigid ball of electrolyte molecules with a tiny little lithium ion in the middle of it. And you're not moving your tiny little lithium ion, but that whole ball. And with sodium, the forces that are pulling them towards it are lower. And so you get a kind of squishy ball, and that squishy ball can move much faster. And so that's why you get, in general, of course, it depends on the details of each single battery cell chemistry. In general, you get much faster charging speeds and also higher power. You can almost always use them at much lower operating temperatures than your typical graphite cells. That's a matter of the electrolytes that you have to use with graphite. Graphite you cannot use properly in a carbonate with graphite. That was one of the compromises. It simply destroys the graphite, and that so you have to use high melting point electrolytes that are then diluted with very low melting point and low boiling point electrolytes. That makes everything a lot worse, also much more flammable. That is the reason why some of the lithium-ion batteries can easily burst into a fireball when mishandled. Yeah, obviously cheaper materials everybody has been talking about. I don't think I need to elaborate on that. You can also fully discharge them, and it's not a safety risk. That's because you can use aluminum in the anode. You don't need copper, and copper has the unfortunate tendency to dissolve into the electrolyte when you reach 0 volts. And with aluminum, which is also cheaper and lighter than copper, you don't have that problem, and so you can go down to 0 volts without a safety risk. It may be a technical problem, you may lose performance, but this really depends on the chemistry once again. Yeah, next slide. Yeah, you have a lot of different chemistries. The anode for the moment is more or less settled. Hard carbon is being used, although there are different kinds of hard carbons, different ways to make it, different precursors. My favorite from the research was always carbonized spring onion peels. Obviously not very scalable, but there are much better scalable things like I think Hynise using coal, for example, anthracite coal as a precursor. And there are many other precursors, a lot of them derived from biomass. And several others. As for the cathodes, you have you have layered oxides, transition metal oxides. This is similar to NMC. In general, they are very high in density. They provide the best energy density also by weight, if you look into the science. And there's a second category that is polyanions. The polyanions, you know them, it's LFP. LFP is a polyanion, it's a phosphate. Polyanion simply means you have at least two kinds of atoms alongside the metal that you're using. So it's iron phosphate, so you have iron and you have phosphorus and oxygen in there. It's not a metal and just oxygen, for example. It's a very diverse group. Some of them can provide very high power. Some of them are quite low cost. You can get very high cycle life because polyanions leave more space in between, can be very rigid and stable. But it really depends. It's very varied. And Prussian blue, I sometimes call it the LFP of the sodium world. It's not quite true, but almost. It's very similar in energy density. By weight, by volume, it's bigger. But it has overall very nice profile of capabilities, which is why CATL announced it as their first chemistry. Although I think they ran into a little bit of trouble getting permission to make it. Production requires hydrogen cyanide, which you then have to just for the synthesis. After the synthesis, it's perfectly harmless, but during synthesis, you need it, and yeah, that required even in China, you need licenses to make large amounts of hydrogen cyanide, and that yeah caused them to stumble a bit, and I don't know, delayed it a few months or so. Yeah, next slide, please.
So I'll take over for this one, and thanks Frank for putting the
Yeah.
context in, the history. Sodium ion is not new. It's gone through a very similar development pattern to lithium ion, and also has a variety of shapes and sizes similar to lithium ion that can address different end uses. Now, for the next part of the webinar, we're going to look a little bit more about the go-to-market story for sodium ion. Now, to do that, we first need to understand where is the market today. Well, most of you will be familiar with charts like this, looking at the current makeup of cathodes, particularly in the EV space using lithium ion. Now, the chart on the left-hand side is basically a combination of all the announcements from about 170 different cathode operations, both in operation and in future operation. And I've grouped those just into two categories. The first is those cells which are designed for cost. They're there to be cheap. They're entry model units. That's typically LFP and increasingly LFMP type cathodes. And then you've also got the designed for performance. So these are your 300-mile range plus vehicles that are typically using an NCM 811 type battery now. And you can see that, if we look at those forecasts, it's about 50-50 on the market side for EVs at the moment. This is reflective of what's been announced at the moment. Those plans can and probably will change. That's where we are today. What we've done on the next chart is just show, our growth forecast at SC Insights for the battery market from transportation, from energy storage systems, and from portable electronics as well, excluding lead acid and alkaline batteries. So effectively, what we've done with the red line there is look at what the addressable market for sodium ion is. You're not going to put sodium ion into a premium vehicle. You're not going to put it in, it's not going to be in your S-Class Mercedes, etc. But it can take a large amount of market share away from LFP, away from LFMP as we go forward, and we'll look a little bit at production costs going forward. So the red line there shows what the addressable market, the sort of theoretical addressable market is for sodium ion. Last year, you had probably about 1 gigawatt hour of production. And by the end of this year, you'll be close to 10 gigawatt hours of production capacity in sodium ion. When we look at the announcements that we see, quite credible announcements in China, you've got about 140 gigawatt hours planned from these companies alone. Other estimates show there's up to 400 gigawatt hours in the pipeline, although some of that's a bit less credible in terms of what can be deployed. But it does look like, the option is there to switch quite a large part of the future supply chain into sodium ion. And at the moment, it's the China story. Even though, as Frank, showed very well in his slides, a lot of the development was done in Europe, a lot of the development was done in the USA. At the moment, the orders are being placed in China, and most of the development and investment is happening in China. And a large part of that is because outside of China, it's very difficult to get financing for these operations unless you have a long-term offtake contract. So none of the big battery plants which are going up in Europe and the US have been built without long-term offtake contracts. And it's the same for a lot of the cathode supply, chemical supply, lithium supply as well. So without people saying, I'm going to buy 4 gigawatt hours of sodium-ion batteries, it's unlikely we'll get the plants financed. And that's why a lot of the rest of the world and European projects there have stalled a little bit. They would have been shovel ready a couple of years ago had they received the financing. In China, it's slightly different, and they're stealing a bit of a march there. Just going back to the Europe and US side, Frank, you wanted to talk a little bit more about the history here.
Yeah. Short note on the history, sodium-ion batteries, as I said, John Goodenough developed Prussian Blue in 2010, and by 2012, there was a grant, an ERPA grant to develop that into a full battery. And by 2015, this had been done, and they basically use standard equipment. That's true for all sodium-ion batteries. Sodium-ion batteries are not a completely new technology or something like that. It's extremely similar. You really just use different salts. You use sodium salts instead of lithium salts, and otherwise the construction is basically the exact same. You use industry standard equipment, and you scale up your chemistry from laboratory flasks to demonstration reactors. And then that's usually the point when in the West, the funding ran out and it couldn't be scaled much higher. A very similar story played out with A123 with LFP, and LFP was more or less abandoned in Europe and US and moved all the way over to China. And it's the same with sodium. Sodium was a Western story until funding ran out and no investors showed up to keep on developing. So all the chemistries we see right now are all drop-in replacements for lithium-ion batteries. You can basically use the exact same assembly plants to build your cells. You just need different materials. That's as much by design as by accident. if you don't have the funding to build your own factories, obviously the only chance you have is to develop your chemistry in a way that is as fully compatible with what already exists as you can possibly make it. Now that funding is there, a lot more funding, we will also see much more specialized facilities and equipment, and this will also translate into better performance of these batteries, and we will see this in the next couple of years.
Yeah, so looking at what all of this means in terms of, are we going to move to sodium-ion? How quickly are we going to move to sodium-ion? The big advantages on cost. Obviously, that's not the only metric that you judge a battery for, and you put it very well, Frank, when you said that everything's a compromise and a trade-off in the battery side of things. Now, if we look at the production costs from the lithium-ion battery sector at the moment, we'll group that into the ternary cathode materials and LFP for simplicity's sake. We did some modeling on a previous webinar where we looked at what are average costs today. Just a caveat, there are many different ways to measure costs, so this may not be the same as everything you see in the newspaper. But we looked at what the theoretical minimum was, taking into account that these raw materials need to have a certain price to actually come out of the ground. You're dealing with finite resources when it comes with raw materials, so it's not like you have necessarily a learning curve where you constantly get cheaper over time. We can't make that assumption when it comes to raw materials. So when we look at the nickel, cobalt, manganese side of things, you could theoretically, in a very cheap market where there's ample supply of all the materials and where raw materials are significantly cheaper than they are today, you could get down to the mid-60s in theory. Probably we won't get there because it would be very difficult to bring that raw material to market and still make those price points. The majority of the price declines we've seen in battery manufacturing and the economies of scale are behind us already. You're really looking at incremental improvements now. Situation with LFP is slightly better because you have cheaper raw materials going in the first place. So a lot of people say LFP batteries you can buy at the moment for $80 per kilowatt hour or so, which doesn't take into account the actual price that you would pay for the cell. But that could again go down to about $60 per kilowatt hour in the future. It makes them very attractive for most vehicles. It puts you within price points very similar to internal combustion. So the premium for electric vehicles should come down, and that will again help with adoption of these vehicles. But as Frank said, we're getting a little bit closer to sodium-ion now to being able to compete with LFP on a specific volumetric energy density basis. Obviously, there's some other hurdles, there's some pros, there's some cons, but the big competitive factor that it has is on the price. And Frank, I'll pass over to you to talk a little bit about production costs and pricing for sodium-ion.
Yeah, right now it's kind of difficult to take the prices that are announced, that are shown on the market, because everything is very small scale, and small scale means you don't have the economies of scale that you would normally have, and so you really have to extrapolate to the future. What we will see with sodium, because some of the components are simply not there, like the copper foil, which is a fairly expensive component. So you can save some components, and what you also see is so some of the cathode chemistries are much easier to work with compared to either LFP or NMC. So you can have cost advantages across the whole production line. And I think in the future you can still remove some other components that will result in a further price drop, but this is much too early to talk about right now, to say that prices are definitely going to go down even further than what has been announced. And you typically hear announcements and on the order of 50 kilowatt hours, maybe 40, some are even lower than that. That's for the next couple of for next generation or this generation chemistries when they are fully scaled up, which is obviously not yet the case. So this is a discussion that's a bit theoretical, but we have all seen the price drops in the last decades. They can be very astonishing, very surprising, far down, and I don't think that $40 to $50 per kilowatt hour are the last word on the cost of batteries. And this is also going to be important for electric cars, because my first car was a Suzuki Alto. That's a $5,000 car, range about 500 to 600 kilometers, obviously internal combustion engine. But if you want to match that with electric vehicles, you need much cheaper batteries than you have right now. Next slide.
And we've seen, yes, it's probably going to compete on cost. There's a lot more to go in that journey. We've had billions and billions of dollars invested in the lithium-ion supply chain. A lot of people won't want to write that off. It's not fully depreciated yet. Most of it isn't even built yet. How quickly do we think that sodium-ion can make these inroads? And this is a thing where we get to the crux of the market disruption. And Frank, I know you had some opinions here.
Yeah. Well, we will see. In the next couple of years, 1 or 2 years, there will be very large growth. We have seen this with LFP. It's dangerous to underestimate the growth potential of new battery chemistries. As we have seen time and time again, also with NMC 8.1. I remember that in 2018, people were arguing that NMC 8.1 wouldn't be properly on the market until 2025. It's 2023, and it's an old hat. Market disruption is something that really happens. It's not just a buzzword, and it's really worth going back to the original papers that were published in Harvard Business Review, which makes it fairly clear that the point of disruption doesn't happen from the top. It's never, you don't see a market being disrupted by a technology that's better than everything that's on the market. It's always a technology that is worse, and because it's worse, it gets easily ignored by market participants, and so you see a lack of reaction by anybody to a new technology, and that lack of reaction, that is what is leading to disruption. So it's really, that's why it's so dangerous to ignore this kind of development.
Cool. We're getting close to time, and we've got some great questions in there. Please do use the Q&A function. Just before we get there, I'm going to talk through 3 examples where we've actually already had market disruption because of price spikes in the lithium-ion industry in the past decade, and then Frank's got one more as well. So if we go back to 2018, we saw a big price spike in cobalt. There's the famous stories that the OEMs couldn't source their cobalt when they wanted to, because the market was very tight and it had already been sold. Nobody had material to sell to them on a long-term contract. And coupled with the reputational issues with cobalt, and the fact that as battery thermal management systems got better, you could reduce it, increase energy density by increasing nickel. We saw a huge amount of thrifting away from that raw material, and we saw a big increase in NCM actually take up, and that was very much the winning technology. We then started to get issues around nickel, and we saw the price spike happen there, and a bit of a market squeeze happen in 2022. And again, what we've seen in China is a big reaction that actually cost became the sort of limiting factor of the cell in the electric vehicle rather than energy density. So that sort of metric between cost and energy density went to the cost favor, which meant, okay, how do we do that? We get rid of nickel, we get rid of cobalt, and we go back to LFP. And we've seen some fantastic advances in LFP in terms of energy density, and now over the next couple of years, a lot more deployment of LFMP when it comes to the market. Then we get to lithium. You will be familiar with the price spike that we've seen. One thing that's worth pointing out, the changes to deployed cathode materials didn't happen immediately. They didn't happen when the price spike happened. They happened in the years afterwards. These processes take a long time. And one thing we have seen so far in China is that, sodium-ion has managed to attract a significant amount of investment. We've seen CATL testing these cells for years. We've seen a big announcement by BYD recently. We've got many other companies looking at multi-gigawatt hour scale plants. So that impact is there, and a lot of that is associated with the price spike and the risk that we see within lithium going forward. And then Frank, you had one more.
Yeah, actually two. I just with sodium-ion batteries, you also have you basically match the energy density of LFP at low temperatures. That's one of the big advantages, is that in the worst case scenarios in winter when it's really cold, sodium-ion batteries are basically on par or even better than LFP batteries, and that can be a huge help, especially like in places like northern China also. Yeah, and is preferable for very cheap cars that have poorer thermal control and much smaller batteries to begin with, such as BYD Seagull. Cars like that really benefit from that, but also other cars. And finally, yeah, cobalt. Back in 2007 and 8, there was a huge cobalt shortage, and this more or less directly led to the breakthrough of NMC batteries. In 2008, you may remember that the Tesla Roadster still used lithium cobalt oxide batteries, and rather controversial, they switched to NCA batteries, nickel cobalt aluminum cathodes, in the Model S in 2012. Despite the fact that it was thermally very unstable, or I mean, you really need a good thermal management with NCA to make sure it doesn't combust. It doesn't. You don't get a thermal runaway when you heat it up too much. Another advantage of sodium-ion batteries. With lithium, the self-increasing temperature starts at about 90 degrees. With sodium, it starts at about 120 degrees, so you have a much more leeway there. And with that, we will conclude, right?
Yeah, we've got a great number of questions and some really good questions to go through. So I think I'm just going to leave we won't go through this slide. I'll just leave it up there for a bit, and you'll get the summary anyway. So we'll just go straight to the questions, and both myself and Frank will attempt those. So the first one is graphite and copper not needed for sodium-ion batteries. That was listed as a pro for sodium-ion.
Yeah, graphite is not needed because it doesn't work. That's very simple. Copper, unless it's part, for example, of your cathode chemistry, some of these cathodes use copper. Other than that, it's not needed, and will be avoided for obvious reasons.
Cool. Then we've got a question on volumetric energy density, and I've noticed this. It's very easy to find the gravimetric energy densities, but it's always sort of conspicuous by its absence when we see the volumetric energy densities, and obviously when we're dealing with transportation, that's a huge limit to how many cells you can put into a pack or vehicle. Any comments there, Frank?
In general, for the same gravimetric energy density, it's like 10% less or something like that in practice. It really depends on a lot of other factors. Cell construction is a major factor there, whether it's cylindrical, whether it's prismatic, what kind of prismatic. You will also, it depends on the materials, what kind of material, what grade of material, especially with the hard carbon, which is a big factor in determining the volume. Yeah, it's difficult, but you can see very reasonable figures there. That is basically on par with LFP within 10% or something like that. You can use the same kinds of highly efficient battery packs that you can use with LFP, and so this is actually not much of a problem. Also, look at cars these days. Cars get big, you don't really have a problem with volume.
Well, you still have parking spaces.
At least when you design a new car from scratch, you can always design the battery pack to fit the battery you need.
So,
especially in the low-cost market, the problem is more how many cells can you afford, then how many can you put into the car.
A great question here, and from what we've seen so far with the announcements, is the majority of sodium-ion capacity is going to be new build capacity. The question is, can a gigafactory swap from making LFP to sodium-ion?
Yes.
Are we going to see the displacement?
Yes, that's possible, and that makes it very difficult to say what the actual production capacity is.
Yeah, and it's worth mentioning, there are organizations, I know in Germany, looking at, can they use the same equipment on these lines? Can they make those changes? There's a lot of work going on behind the scenes that actually will set the ecosystem for sodium-ion going forward. So again, it does potentially mean that this shift could happen a lot quicker. Quick question here on the cost slide, comparing 811 versus LFP versus sodium-ion, is that at the cell level? Yes, it is at the cell level. And then the question, when we're comparing on the cell level versus the pack level, is there any difference that we should be aware of for sodium-ion versus lithium-ion when it comes to the sizes and density?
LFP level, comparable to LFP in that regard. The differences, at least. Going forward, we will have to see the exact development of the chemistries.
Yeah. Then obviously we've seen some quite large declines in lithium prices recently. Will
Do you still hear
sodium-ion.
me? My camera switched off for some reason.
We can hear you, but
Okay.
your head is paused. So we'll
Yeah.
see what was that. So lithium prices have come down by 2/3 over the course of this year, and the question is, are lithium prices going to at a lower sub $20 per kilogram level? Is that going to impact sodium-ion penetration? I mean, the obvious answer is it will have an impact because lower lithium prices means that you can design to a lower price point for the vehicles, which is very important in the entry level models. But at the end of the day, the sodium is $200 to $300 a ton versus $16,000 or $17,000 a ton for lithium.
Yeah, and it's not just that; it's also the other components that you can save on, like the copper current collectors, and keep in mind that sodium-ion batteries are much better in several qualities, several of the other qualities like temperatures, like safety, like charging speeds. Those charging speeds have been achieved without any tricks at all in a very low-cost cell, and this will get better as time goes on. Yeah, as we see here on the slide, cost parity is more than sufficient to be competitive with lithium-ion batteries.
Question
also,
here.
lead-acid batteries are still selling despite 35 watt-hours per kilogram. They're still selling, and they actively compete on in the two-wheeler market. When prices went up, NEU, which is the largest manufacturer in China, started to use more lead-acid batteries instead of lithium-ion batteries because they just became too expensive. Yeah, so energy density doesn't matter quite as much as you would think.
We've got a question here. When we looked at the anode side for sodium-ion, hard carbon is the leading material being used. That limit or any other parts of the supply chain limit deployment of sodium-ion
Not really.
owing to capacity constraints?
Currently, yes, but in the long run, not at all. There's plenty of precursor material. I mean, carbon is it's not like graphite. You don't need a specific allotrope that you have to mine or synthesize. You can just use almost anything. It just then depends on exactly what kind of processing steps you have after that, what kind of performance you can achieve.
All right, the next question is going to be a bit of a test for you, Frank, as a leading proponent of sodium-ion. And it's that, is there an opposing view to this? What are the risks to sodium-ion? And I'll give you a shot at that. What could stop sodium-ion coming in? And if you can't think of anything, I'll give an answer.
Well, in the short run, it's obviously the lack of experience with it. In the long run, in the very, very long run, I would say that theoretically magnesium and calcium ion batteries, which are not yet ready for prime time, could be better than sodium ion batteries, especially in combination with sulfur. But we are not there yet.
Yeah, and I think I'd add that in some respects, certainly outside of China, the market isn't ready for them. You know, we're still deploying the high range, high nickel cells. That's what the majority of people want. They want the 300 miles rather than the 200 miles from LFP, or comparable potentially from sodium ion. So that's going to delay things.
I will give a shout out to Northvolt, who have recently announced one of the batteries, sodium ion batteries, based on Prussian white or Prussian blue. It's a Prussian blue analog. It turns white when it's fully loaded with sodium, which means it's fully discharged. And when you charge it, you remove the sodium, and as soon as you remove the sodium, it turns blue. So that's why it's always called Prussian white, because that's the form that you would want in your cathode.
I can tell you, having worked on the Northvolt financing several years ago, they would not have got the financing without the offtake contracts. And while they have the technology for sodium ion now, they don't have those offtake contracts. So, there's no commercialization plan yet.
Yeah, that's possible, but I see them putting all their ducks in a row, also on the anode side.
Yeah. And it's worth mentioning, most of the large cell producers in, Japan, South Korea, and outside are looking at sodium ion as well. Let's say, I think the market in 3 to 4 years' time will be much more receptive to having different chemistries of batteries. So this isn't something that's going to happen overnight. It will happen first in China, and we've still got a couple of years to run, see how successful they are in China in terms of deployment, because we're only just getting to the deployment into not quite branded vehicles, but sort of new vehicles in China. So it will take a while before that happens. And even BYD, who've made one of the largest announcements and investments in sodium ion, albeit in a partnership, still very much focused on lithium ion, as I see it here. So this isn't an overnight change. You've also got the billions of dollars of undepreciated assets, which aren't going to go away over the coming few years even.
Yeah, I think it's as I've said for a few years now, it's going to be LFP all over again. Just a repeat of that old story.
Cool. Then a question on the recycling side of the market. As of 2026, the demands that 60% of the weight of any battery needs to be recycled. Can this be achieved for sodium ion? And that's a good business case given the lower raw material hits from recycling.
Well, if there's a law, it will be done. Lead acid batteries are being recycled, even though it's not always economical to do so, to a very high degree, some 99% or so. And especially when you have these large battery packs, you get them very nicely in large chunks. So I do see this happening because the law will say it has to happen, so it will happen.
Yeah. Yeah, and
it
there'll
really
be
depends on.
legislation.
Also, it depends on what kinds of chemistries you use on the anode and cathode side, how useful it's going to be, how expensive the materials will be. It really depends. It's not very simple. Most of the chemistries are obviously developed to be as cheap as possible right now, but that's not true for all of them. You can get extremely high power batteries, for example, and there you will use. There you're free to use much more expensive materials.
There's a slight follow-up to that, looking at recycling and the materials included. Question here: due to the risks of HCN intermediates, is there any chance of sizable Prussian blue analog production in the EU? Are there any disruptors there when it comes to the types of raw materials that we're using?
I don't know the regulation there. You need HCN, hydrogen cyanide, to react with iron to get Prussian blue. once this reaction has happened, it's really perfectly harmless. You get Prussian blue, and Prussian blue is even used as medication. You can just take it, and it's used to remove metals from your blood. For example, if you had radioactive cesium in your blood, then you would take this, and it would take up the cesium, and you would pee it out. You would get blue pea, which is that's about it.
Cyanide's got the same classification as lithium now.
Yeah,
the
the problem with cyanide is that you don't want to have the cyanide itself, the hydrogen cyanide in your blood, because when you mix hydrogen cyanide with blood, it turns blue. That's how Prussian blue was actually invented. They mixed pig's blood with hydrogen cyanide and turned blue. Was the first artificial blue color, and that's how it got its name. And that's the dangerous part, actually, because you need that iron in your blood to take up oxygen. And when this reaction happens, the blood can no longer do that. It's very similar to what carbon monoxide does.
Then, somebody asking about the percentage decline of lithium prices. At what price does a lithium carbonate-based LFP battery become better than a sodium-ion battery?
At no point.
I don't know the exact answer to that off the top of my head, but I can pretty much. There's a few variables. It would be substantially lower than now, and the lithium-ion side is not really competing on cost, and you would probably be getting below if not the production cost, certainly the incentive cost or incentive price to bring more lithium-ion to market.
Especially with Prussian blue, but also with some other chemistries, you will definitely have lower cost, no matter what. That doesn't depend on the price of lithium. It's just the general cost of making the stuff is just lower, of making the stuff and using it.
Then could we comment on the charge and discharge profile of sodium-ion and how that changes in voltages and affects its usability in both EVs and ESS?
That depends. As usual, it depends on the chemistry. Layered oxides do have a problem in terms of a problem. They have a larger drop of voltage, but other chemistries are perfectly fine. Also, it really depends on what exact chemistry you have. There are so many out on the market that it's impossible to comment on each single one of them. You really have to look at the discharge curve of every single one of them and then come to a conclusion. You cannot say anything like that about sodium-ion batteries as a whole. It's just impossible. It's a large zoo of different chemistries, like the nickel batteries that I've shown at the beginning.
Yeah. Then we're not going to have time for all of the questions. We'll do another couple before we finish, and then we will follow up with offline with the ones that we don't get round to. So just two more quick ones. China are probably supposed to be having their sodium-ion battery packs deployed. I think by the end of this year, we're running out of time unless you're looking at the Chinese year. Any updates on that, Frank, as to deployment in EVs of sodium-ion in China?
I don't have them right now. I don't know right now. Sorry.
Yeah, I looked at it recently and it was still this year, but I haven't seen it.
That was my information, but I don't have any updates right now.
Yeah, and I say it'd be something to closely watch because if there are performance problems there, then it's going to limit uptake, the sizable influence on the market down the line. We'll see if we've got time to put one more in. Okay, so why is Northvolt advancing a Prussian white over other flavors of sodium-ion?
Because it's the lowest cost, and you can locally source all the raw materials for it without any issue whatsoever. And it's very decent in terms of energy density. Okay. Sorry, I didn't have time to look at the Q&As myself.
That's all right. I think we'll leave it there. Actually, there's one more. What's the scope of sodium ion in India? And really interesting one, because there you have Reliance,
I
who
would,
bought technology from Viridian,
yeah.
and they just announced a very large LFP plant. So it's not a clear cut decision at the moment. And I think perhaps we'll leave it there. So thank you all for
I will,
joining the
I
questions.
will address one question.
Great.
Yeah, soda ash is sodium carbonate, and that's basically used in almost every cathode material as a precursor. So yeah, sodium carbonate, you can find sodium carbonate and sodium hydroxide all over the lithium-ion battery chain as well. It's quite incredible. People have asked a lot if it's possible to get so much battery grade material for sodium-ion batteries, and yes, of course, because it's used all over the place in lithium-ion batteries. If you make
Frank, I know you could go on forever. We are out of time, unfortunately.
all right.
But thank you all for joining. And I say we will get back to those questions we didn't get around to answering on the webinar.
Yeah.